I have been working on ontologies for medicine, biology for many years, and a few years back I started to work on ontology for various military projects. And I'll explain what ontology is for those of you who are completely new to the subject in a minute. Very recently I started working with engineers. And as a result of this, I was invited by the Systems Engineering Research Center, which is a big multi-university government consortium which works in the field of systems engineering. They had been told by somebody, I presume somebody in the government, that they needed to have an ontology of systems engineering. And they approached me because I already had a certain record for helping people to build ontologies. And so I presented some of this material that I'm going to present today in Washington to a group of people from CERC. And it will become very clear that I'm not a systems engineer, I'm an ontologist. I think I know a little bit about systems engineering as a result of my interactions with the CERC group. And I will describe the results of those interactions in a way which is designed just to give you an indication of what building an ontology for systems engineering would look like. I do not have an ontology for systems engineering yet, but there is a proposal for an ontology of systems engineering, which I'll talk about at various points, which has various problems. And I'm going to illustrate some of what I want to say positively by indicating problems in this particular ontology proposal. And the ontology proposal came from the Jet Propulsion Lab, which works closely with CERC, and it's been developed in conjunction with people from NASA, people from the Defense Department, and various other organizations, but the central proposal and the central development comes from NASA. And as a result of this decision that the CERC community needed an ontology, they created something called Semantic Technologies Foundation for Systems Engineering. And this is an initiative which has a charter, which is to promote and champion the development and utilization of ontologies and semantic technologies to support system engineering practice, education, and research. So from this you can learn that ontologies have something to do with semantic technologies, and I'll explain what that means also in a minute. The foundation is meant to bring together various groups in order to build a consensus around a specific ontology proposal, formalize this consensus using formal ontologies, and then promulgate methodological guidance for how to use this ontology and connect it to related ontologies from industry and academia. And I'm going to talk about all of that in the course of the next 6 hours. So Steve Jenkins is the leader of this initiative. And then you can see I'm involved as a consultant to the core team. I am the director of the National Center for Ontological Research, which is based here in Buffalo, which has existed for some 12 years, and which, as I say, has been involved in various military and other initiatives with colleagues both in Buffalo and elsewhere. I think I can say that Buffalo is one of the 2 or 3 principal centers for ontology research in the world. And you can gauge whether that is true if you Google the word ontology and then see how much of what comes back is based in or derives from work in Buffalo. So this is the original agenda, and I'm going to try and stick to it, and you have a schedule in your hands so that you can see how well I'm doing. There is a very, very crude distinction between natural systems such as the solar system on the one hand, and a lot of biological systems on the other hand, which I will be talking about in the course of the day, and then engineered systems. And the principal focus of the CERC initiative is engineered systems, but they view engineered systems very much from a social organizational point of view. And I will explain what that means in a minute. But you can see part of what it means if you understand that their principal example is the Mars mission. Now, in order to get to Mars, we're going to need spaceships or rockets. I don't even know what the correct word is for the things that we're going to send to Mars, but we're going to need some of those. But just having those is not going to get us to Mars. In order to get us to Mars, we're going to need human beings. And those human beings are going to need to be tremendously well organized. And that's where systems engineering comes in. Not just organizing human beings, but organizing human beings working with material systems, engineered systems like spaceships and launch pads and so forth. Now, I think that the crucial dimension, and this is why the discipline of systems engineering arose, is the fact that these kinds of systems, at least, can fail. So the Mars mission can fail. Your digestive system will one day fail. And the hydraulic system in your car may fail. So it's a characteristic of large and complicated systems that they have a high likelihood of failing unless you work very hard to ensure that they do not fail. That is why the discipline of systems engineering came into existence, because of this problem of failure. Now, there are other kinds of systems, and I'm just going to mention one, which is the decimal system, but there are many software systems. IBM has a system for making money. There are, I'm sure, tantric systems for curing Vedic diseases. I'm not interested in those uses of the word system. They are not uses of the word system which are important for systems engineering, and I do not believe that it's profitable to look at the ways in which purely informational systems like the decimal system or the Library of Congress catalog system might somehow be connected to the kinds of systems I am interested in, which are the ones that can fail. And that doesn't mean I'm not interested in information and software. The Mars mission is going to involve huge amounts of software, for instance. So the sorts of systems that we're interested in will be what are sometimes called cyber physical systems, which means that they have software aspects and physical aspects, but they're also going to be social systems. They're going to have human aspects. All right, now this, there are various places where you can go for information, glossaries, for instance, of systems engineering. One of them is called CBOC, and CBOC talks about natural systems. It says the real number system is a natural system. I'm not quite sure about that, but they do mention the solar system and so on. They don't mention biological systems. And then they talk about social systems, like, for instance, the foundation for semantic technology in systems engineering. That's a social system, as some would conceive it. As I say, many of the examples that we're going to be talking about will involve a social aspect. They will have human beings as parts. And then technological systems, I think man-made artifacts or constructs, including physical hardware, software, and information, they are the systems that we're primarily interested in. And that's what the Mars mission system is. Another organization which is important as a source of information on systems engineering is INCOS. And that's incos.org. They also have a glossary, and I draw on some of that later on. Now, this is my favorite example of a system. This is the hydraulic system in your car. I don't know anything about hydraulics or cars, but I know that that's a system. And it's a material system. It's made of material stuff connected together. But the material stuff, well, first of all, it's connected together. That's an essential aspect of systems. They are connected together. Secondly, the elements of this system are such that they have functions and capabilities. They can do things. So if you arranged inside your car 5 pieces of equipment and connected them with pipes and wires randomly, you would not have a system. So this is not just any old connected group of elements. It's a connected group of elements with capabilities which have been connected together, the elements, in order to achieve something. So that's the first rough definition of what a system is. Now, systems engineering started in the 1940s in Bell Labs. It was very closely connected with the war effort. And the principal supporters of the discipline of systems engineering ever since have been the military. And the reason is that the military often fails. So the military has huge numbers of systems and systems of systems. The military often goes through periods of disastrous failure. Drug use in Vietnam, for instance. In every such period of disastrous failure, more money is invested in systems engineering, because they think that by working very hard to understand how to create and maintain systems, they will avoid failure, or they will reduce failure. Now, this makes systems engineering quite different from manufacturing, for instance. In manufacturing, failure isn't really a problem. You're trying to produce a product, very, very narrow focus, few dimensions along which failure can occur. Once you have the product going, then it just keeps going. The production process just keeps going. Systems engineering is about complicated processes which don't just keep going because they have too many dimensions of variation. So, systems engineering tries to discover the problems that need to be resolved and to identify the most probable or highest impact failures that can occur. All right, now we come to ontology. One failure, I'll give you an example of one very important failure. The Airbus project was a joint European Union, mainly France and German, product to build a gigantic aircraft. The aircraft had a wiring system. They built it in 2 halves. The front half, I think, was built in Toulouse, and the rear half was built in Hamburg, or vice versa. And then they brought the 2 halves together. And then they had to thread the wiring through the joint area. And they discovered that the holes were too small to enable the wiring to go through. And that cost, I think, 26 billion euros to fix. That was a failure. And the failure arose because the way in which holes with an H were being described in the systems used by the Germans was slightly different from the way in which holes with an H were being described in the systems. And by that I mean CAD systems, computer-aided design systems. They had the same CAD software, but they used different versions, roughly speaking. And the one version treated holes as 3-dimensional, the other version treated holes as 2-dimensional, roughly speaking. And that caused a slight millimeter size difference in the calculations of the holes by the 2 groups, which led to basically the redesign of the entire wiring hole system. Now, that sort of failure is a result of one word having 2 meanings. Ontology is the discipline which attempts to avoid such failures by making sure that every word has a single meaning by focusing on correct definitions of words. And so we have a methodology for writing definitions, and we say that this methodology is designed to promote interoperability. That means working properly together across heterogeneous data systems, which means the French CAD system and the German CAD system, for instance. And the way it works is by exploiting the fact that natural language changes relatively slowly, while hardware and software, given the pace of change in computer technology, change very rapidly. So you have too many databases, too many different codes for the same things. You put those databases together, you run the risk of failure. If you have an ontology, you can use the ontology in order to mitigate that failure. All right, now, that's just repeating what I said before. So the reason why the government, or whoever it was, called CERC and said you need to have an ontology is because the government has faced so many cases where too many databases which differ from one part of the government to another, or from one company to another, are forced to play nice with each other, and they don't. And people don't realize how hard it is to make databases created by different groups, how hard it is to get those databases to play nice with each other. Or maybe people in the room do know. A lot of people do know. All right, so this is this is a fragment of the ontology built by the Jet Propulsion Lab, which I'll talk about later. So a component performs a certain function. A requirement specifies a certain component. The mission would be the Mars mission, deploys a certain component, and so on. That's the kind of thing which an ontology does. It takes terms, typically terms from natural language, sometimes terms from specialist languages like genetics, and it links them together with relations. And the idea is that all of these things are defined, and then you have a database over here which has various components in it, and you have another database over there which has various components in it. This database uses French, this database uses German, and the ontology uses English, which is the language that is used typically for these things. All right, so how did it start? Ontology has a very ancient history. It goes back to Aristotle, basically. But the use of ontology in computational contexts began in around 1970 in Stanford. And I'll talk a little bit about those early beginnings. I'll then talk about the Semantic Web, which is the most influential set of ontology initiatives within the computer world today. And then I'll talk about the biology use of ontology, which is the principal area where I started working on applying ontology. So this is strong AI. How many people in the room know what first order logic is? Not very many. So in the 19th century, people showed how to formalize logic. Before that, people knew how to reason logically, but they didn't have a formal system so that they could check complicated reasoning, for instance, using a computer. The first formal system, which is still the standard formal system, is called first order logic. It has a very nice property that you can reason with it, you can formulate proofs, you can have axioms, theorems, and you can prove that the theorems follow from the axioms by very rigorous methods. And it's very, very simple, and it's very easy to use. The problem is the proof methods are not decidable. And what that means is that if you try and use a computer to prove theorems using first order logic, the computer may never execute. It may just take an infinite amount of time, and that's embarrassing. Now, but still, in the early period of strong AI, they only had first order logic, really. It was the standard logic. And so they thought they faced the following problem. If we want to build an artificially intelligent robot, we need to teach the robot what humans know about the physical world. Chairs, tables, bananas, and so on. And so, how do we do that? Well, they thought we should translate all the things that humans know into first-order logic and then feed the first-order logic into the robot. And then the robot will be able to buy salad or peel a banana. That was a very serious enterprise for some years, starting in around 1970. And the first really interesting contribution that came out of that effort was the realization that you need to be able to exchange content from one computer to another or from one person to another. And the standard language for first-order logic in those days was not suitable for exchanging content. It was, you could write it by hand, you could even print it, but it was hard to program with it. And so they created what they called knowledge interchange formats. And one of the principal leaders in this field was Tom Gruber, who is almost certainly the leading grandfather of modern ontology. And Tom Gruber is important today because he is the chief designer of the Siri app in your iPhone, which is based on ontologies. So you all, or nearly all of you, have ontologies in your pocket. Ontologies for restaurants, films, traffic jams, and so on are used in order to make Siri work. Now, in 1985, Patrick Hayes, who is another leading figure in this Stanford movement, originally a philosopher, wrote something called the Naive Physics Manifesto and created an ontology for liquids, both of which were important stepping stones towards what we nowadays think of as applied ontology. And by 1995, people were trying to apply this in engineering, and they failed terribly. In fact, these things, apart from Siri, which came much later, all failed terribly. And then there was something called the process specification language, which is still a working concern, but it's not very much used. And these are some examples of the engineering ontologies which were created. So there were many, many engineering ontologies created in the United States and in the European Union, which was very keen on the idea of ontology and spent a lot of money on ontology. They all failed. It was all wasted. Hundreds of millions of euros were wasted. Just to give you some idea, the process specification language, the idea is that a large company is going to have lots of processes, and these processes need to fit together into chains. And the idea would be that if you could specify the processes, you could work out how to chain processes and use computers to make sure that processes were being chained correctly. And just to give you an idea of the ontology around PSL, there are 4 top-level terms: activity, activity occurrence, time point, and object. And the definition of object is interesting. An object is defined as anything that is not a time point or an activity. That definition has serious problems. And if you think about it, a concert performance would be an object. I don't want to go into details, but I think it should be obvious that there are dangerous implications of that particular definition. This is an ISO standard for industrial data, or this comes from an ISO standard for industrial data. Another example is ISO 15926. It's a standard for industrial automation systems and integration. This is what we're all about here. Interoperability and integration are two sides of the same coin. You can only integrate if you have interoperability. ISO 15926-2 has an ontology. I'm not going to go into any details because you couldn't read it anyway. I'll just show you the upper ontology, and this too is very strange. So the top level term in ISO 15926 ontology is possible individual, and An actual individual is a possible individual, which is reasonable enough, but then there are things called arranged individuals. I have no idea what that might mean, particularly if they're not actual. So, why did all these ontologies fail? Well, first of all, this was early in the development of a very complicated discipline with a very complicated challenge. They didn't have a common methodology. They were all trying to blaze a trail, and they were all going off in different directions. Secondly, they were funded largely by things like European Union projects, and as soon as the funding ran out, people lost interest in the ontology. Thirdly, the link between data and ontology is very difficult to get right. If you try and build an ontology on the basis of the data you have, or on the basis of the database language you use, it's very unlikely that the ontology will help interoperability between your database and somebody else's database. So you need to find a level which is database neutral, and they didn't know how to do that in many cases. That's particularly true of ISO 15926. Then they didn't really understand how to write definitions, and they often didn't care to write definitions. It's hard work. So the consequence is that they all failed. They were just never used. There is not one single example of an industrially successful engineering ontology from that period. So the next step is the semantic web. And this was a term coined by Tim Berners-Lee, who, as you all know, is the inventor of the internet. And he created a goal for the future of the internet, which would basically have ontologies built into the infrastructure of many important components of the internet related, for instance, to science. The idea would be that everybody would use, when formulating their scientific data, something called the Web Ontology Language, or OWL. And then software was created for OWL. OWL is decidable. It's a fragment of first-order logic which is decidable. And that makes it very useful for computers. You can build ontologies using OWL, and then using the decidability feature, you can check for consistency automatically. There are tools, particularly Protege, which is an open source tool for building ontologies, which is very easy to use. It's a little bit subject to bloat, but still it's very easy to use in order to create ontologies experimentally. And then you can check whether they're consistent, which is a very useful thing to be able to do. This led to ontology proliferation. Now there are not just dozens of ontologies, there are thousands of ontologies. And this led to the question, well, how do we link all of these together? And this created something called linked open data. This is 2009. And you can see that there are various biological ontologies. The gene ontology is very important for the story which follows. But then there are also, in the same big hairball, actually this isn't very big, it's only 2009, which is epochs ago. Then there are also various very peculiar looking rock music band ontologies in the same, and it gets worse. So, and all of them are built differently. Not just in the garage by teenagers with guitars all around the wall, but some of them are built by serious scientific institutions, but they all do it differently. And this is 2017. So the idea would be in the original conception that there would be a small number of ontologies to create interoperability between databases. Now you have a huge number of ontologies, and you have the problem of creating interoperability between the ontologies. So you've made the problem worse. And there are various groups, ontologies for linguistics, ontologies for government, and so on. And then there are links between them, but the links may just make the links too may be of very different sorts. The same term might be used in two different ontologies. If you're lucky, it will be used with the same meaning, but you're not always lucky. Now, one important part of this is called BFO, which is basically linked to all the biology and medicine parts of the linked open data, and now increasingly to other things. But BFO is a very important item within this hairball, for reasons which we will see in a minute. Okay, now lesson number 3, or lessons from biology, I say here. So this is the third phase. The first really successful ontology, the first ontology which was used massively and profitably even by industry, particularly the drug industry, but also other areas of medicine, biology. It's called the gene ontology. And the problem was that the Human Genome Project created huge bodies of data, chemistry data, molecule data, long string sequences of ACGT, GT, ACGT, and so on. And the biologists needed to use this data, and that meant that they needed to link sequences with words like cell, or cell division, or cell death. The gene ontology is an ontology consisting of those words. And so this is BFO again. That's there's the gene ontology. And then you see various other ontologies. Well, you don't see their names because there are so many of them that there's not enough space. But so the important aspect of the Human Genome Project was not that it was the Human Genome Project. It was that it was a project which could be applied to any organism, including mice and fish and yeast and so on. Now, the sequences in these model organisms are very similar to the sequences in the human genome for all those functions which are common to two organisms. So the digestive system of a mouse and the digestive system of a human are very similar, and the underlying genes are very similar. What this means is you can do experiments using mice and use the gene sequence information to draw consequences for human beings. Now, this is a fantastic opportunity. It's a whole new world of drug discovery. And the gene ontology made this possible because the gene ontology is species neutral. It doesn't contain words for human biology, it contains words for any species biology. And then these words are used to tag gene sequence and protein sequence information. So while each biology community, the mouse community and the yeast community and so forth, had developed their own dialects, the gene ontology created a lingua franca across all species. And so I want to make the following point, which on your agenda is called, actually no, it's not called anything. On my agenda, it's called, how do you future-proof an ontology? The problem with the engineering ontologies built in the 2000s is that they had such a short half-life. As soon as you tried to use them for a new purpose, they just didn't work, and so they dangled and died. The gene ontology is future-proof. And the reason it's future-proof is because it moved up a level of generality. So you have all of these, first of all, the Human Genome Project itself moved up a level of generality. Instead of using mouse or fly or human-specific biological information, it used chemistry, which is species neutral. All organisms have the same chemistry. if you can describe organisms using chemistry, then you have moved up one level of generality. The gene ontology moved up one level of generality when it comes to the terms used to describe the processes and the structures and the functions of organisms and their parts. And that meant that every time a new species had its genome decoded, the gene ontology would still apply. Every time a new kind of disease arose, the gene ontology would still apply. And it's grown and grown ever since, both in size and in amount of data which it's used to tag, which is the key here, and also in numbers of users. So, the Go actually consists of 3 ontologies. One ontology for biological process, one for molecular function, and one for cellular component. So if we just go down the process hierarchy, axis specification is a process which takes place during development. It's a kind of pattern specification, which is a kind of development, which is a kind of biological process. So this is a kind of, or just is the main organizing relation in ontologies. It creates big ontology trees linked together through the link called ISA. There are other links, for instance, part of or regulates in the gene ontology. But the most important link is the ISA link. And you see we're dealing here just with words, but we're dealing with them in such a way that we can define them using relations like ISA to other words. And the more you do this carefully, the more you can reason using the ontology across all the data that the ontology has been used to tag or annotate or describe. All right, and I think this might be a good point to have a discussion. So, are there any questions?
Humans building these ontologies? Is this a manual process?
So the question is, are humans building these ontologies? The answer is, at the moment, still yes. There are various attempts to create ontologies using natural language processing or using other kinds of computer technologies. They still do not yield results which are such that the ontology brings value.
How do you know that you have produced an ontology that gives value?
So the question is, how do you know that you've produced an ontology that gives value? And I think that question is a bit like the question, how do you know that you've produced a scientific theory that brings value? You will only know when you see how your colleagues and your critics and so forth react to it and exploit it and try and break it and so forth. What we do know is that although the gene ontology was created in 1998, it still has the same architecture. It hasn't broken at all from what it had at the beginning. It's become much bigger. Errors have been corrected, but the errors have been errors in single terms or groups of terms. They've not been errors in the way that the architecture of the ontology is conceived. How do we know whether it works? Well, there are thousands and thousands of people using it daily. There are hundreds of statistics programs used in medical research which are based on the data which is created by using the gene ontology to tag data.
How does an error get corrected? Is this there are standard organizations?
Yeah.
Like
So
and other types of
the gene ontology is edited by a group of editors. The way in which errors get corrected is, first of all, that the editors have as their principal job using the gene ontology to tag literature and data about genes and proteins and diseases and so forth. They find errors, and so they correct the errors. The other way in which the errors are detected is by other people outside the gene ontology who are trying to use the ontology, and they have a help desk. The editors have a help desk, and they have an error tracking system. And the the rule is that you should get a response to an error correction request within 48 hours. And the editor's version of the gene ontology is updated every 24 hours.
And how do people, is this on?
No, it's not. You have to switch it on.
And how do people access this ontology? Is this through schemas or like?
So there are many different ways of accessing it, and you find them all online. It's built into many tools now. There are many search engines which use the gene ontology as the underlying search principle, along with other principles. So you can, for instance, if you're interested in doing research, let's say on lung development in children with parents who were smokers, you can use the gene ontology along with related resources. That there is a search engine called Amigo, which is a useful illustration of this, to find all the papers talking about those kinds of children, all the proteins involved in the lung development of those kinds of children, and so forth.
So you mentioned search as one way of consuming these ontologies or getting access to them. Is that process manual or automated? Like, is that process, if a researcher builds something on lungs or whatever, are they then using the ontology and manually tying it back to the ontology? Or are there any types of systems or process that can say, this is the ontology with schema, and I know you're talking about this with this probability, and then do ties that in?
So the question is, how do these links to the data get created from the ontology to the data? There are two ways. First of all, the editors themselves are working daily to create high-quality annotations of biomedical literature. But secondly, there are many, many people now using computers in order to reason across medical literature and across medical data. And many of those tools and many of those projects use the gene ontology as the basis.
But it is manual.
Actually, no. The second sort of annotation is computation. So there is something called the genome. There is also something called the bibliome, which is the entirety of medical literature treated as a kind of gigantic body of data. And the gene ontology is one of the principal tools used for navigating the bibliome. Yep. Can you check that that's working? Just tap it.
Green.
Tap it and see if we hear a noise. Oh yeah, it is one. You just have to shout.
Okay, so, my question is, how do you know you have what I'll call the layering of generality correct? Are there methodologies for doing that? I mean, you said that future-proofing is about selecting the right sort of level of generality, but I think that seems to ripple through the entirety of the ontology, right? I mean, as you select sort of the next layer, you want to make sure that you've got it right. And
So I will be.
There are methodological standards, so to speak, of techniques evolving.
I will be talking about this problem later when I talk about rules for writing definitions, because the way we write definitions is to use the is-a relation. And so once we write the definition, we will have a link in the ontology which maps the definition. But then if we discover that that definition allows children which come between the parent and the child that we've just defined, then we will realize that it's not a child at all, it's a grandchild. So we need to insert a new layer. And I'll show you how that works when I explain the rules for definitions. I think there's another question behind you.
Yes, probably you will talk about this question later on, as you just said about this prior question. But do you know specifically to the gene ontology, how did they come up to these three main branches?
So when you discover a new gene, there are three questions that you are interested in answering. The first question is, where does it live in the cell, that cellular component? The second question is, what biological processes is it involved in downstream, such as cell division, for instance, or muscle development? And then the third question is, how does it do that on a molecular level? So what is the molecular function of that gene? Does it bind to this, or what does it do? And that's the three ontologies. It was the very clever man who made that architectural decision.
It was where, how, and what was the other one?
Where, how, and what? What does it do? So where does it live? What does it do? And how does it do it on a molecular level? There's a question at the back. Shout.
Okay, so what are the processes or sort of educational outreach programs that you would have to perform to include like biologists who aren't familiar with ontology
Yeah.
to use this type of system or to tag their papers with proper terms so that
Yeah, so to get people to tag their papers is hard. People are anarchists when it comes to tagging papers. There have been various efforts by journals to force people to follow rules when tagging their papers, and they've all failed. I believe that the journal article is going to die anyway. Not immediately, but within the next years, because it's too slow. And with computers, we can communicate data more effectively and more rapidly without going through the 1 year, 2 year long process of revision and revising. We just have a lot of data, and we use computers in order to work out which is the good data. That's a sort of dream, but still I believe that that dream will be gradually realized, and that the journal article will become seen as a stumbling block. The same applies, incidentally, to intelligence reports. I think that intelligence data in the future will be much more data and much less reports. Now, the question was, how do we get biologists to tag their data properly using an ontology? I think that's the wrong question. The right question is, how do we get computers to be able to simulate the high quality of tagging which you get from well-trained humans quickly? Because there's so much data, we need more and more of the data to be tagged, and humans can't keep up. I do not know the answer to that question, but a lot of people much cleverer than I am are working on it. Yep.
my question is about, you mentioned about an open source system that we can check the ontology, is it okay
Yeah.
or not? Am I right?
So there are people trying to develop those kinds of systems, yes.
What sort of foundation they are setting? Are they setting some facets? Are they developing some facets to guard, to assess the ontology on the basis of that facets and something?
Do you say phase?
Facets, F-A-C-E-T-S. Facets, it means
F-A-C, facet.
Categories that they will put
Facet.
system in that.
Yeah, yeah. So the term facet comes from the library science community, I believe.
Yes.
And the library science community uses facets to build things like the Library of Congress catalog system. There are people who try to develop rubrics for ontology development analogous to that kind of approach. I don't think that works. And I think that the ontology method is being used in so many different domains. For some domains, facets might be appropriate, but they're not generally appropriate. So it would be wrong to use that as a key to methodological correctness.
Then how this open source system, how that work, what is the foundation?
Oh, that is what this series of lectures today is all about.
Oh.
I'm going to show you how to do it properly. Unfortunately, many people listen to this particular way of doing it. So,
I think you just answered my first question, which is basically, how do you go about creating an ontology?
Yep.
You just borrow from what's out there or whatever. I think you're going to do that today.
Yeah.
That's the first thing. So, my question, though, is the second question is, did they just get lucky with the Genome project, or actually
Okay, good,
Levels or
good.
Something like that, and they just get lucky.
Yeah. So the question is, did the gene ontology just get lucky, or was there some? So the developers of the gene ontology were very clever, and they were wrestling with a very serious problem, which is, how do we poor humans with these small brains deal with these huge amounts of data? We can't deal with it by publishing papers or even books anymore. We need to use computers. How will we use computers in order to do biology? They were facing that question. The early version of the gene ontology is architecturally almost the same as the one we have today, in the sense that we have 3 hierarchies, biological process and so on. But the definitions were, logically speaking, often very questionable. And the definitions are what give robustness to the hierarchies. I think I can say that it was me who showed them how to build definitions correctly. And that led to other things. So once they could build definitions correctly, then they could do other things, which is what I'm talking about here.
So just as a follow-up real quick, the definitions are really key
Yeah.
to building your ontologies. It's not you don't start with
Yeah.
it's the definition.
You start with words, but then very early on in the process, you begin to work out how they relate to each other in a hierarchy, and there you are writing definitions already.
Now, one last follow-up and I'll stop.
Yeah.
So you deal with words, something I guess the biology, molecules, and things like that. I do imaging, and one of the things that we've been stuck with is labeling images
Yep.
for truth and things like that. But now through machine learning, you can have labelless understanding, if you will, quotes, of image information, so as to
Good.
to be able to extract the information and actually determine truth in a different way than we used to think.
Yeah.
So I'm actually seeing an application here in terms of the immense amount of image processing / analysis
Yep.
and their interpretation.
Good. So.
In a proper ontology.
So you and I should talk, because I'm involved in some image ontology work also. But you used a very interesting phrase, labelless truth. Did I hear that correct?
Okay, it should be
No, it's a good phrase, labelless truth. You need labels in the end because you need to use the information in the image in order to. Is this medical imaging?
Yeah.
Yeah. You need words in the end in order to use the labelless truth in the image. The military has a big effort ongoing at the moment, which is it's called meaningful, understandable AI. I've forgotten the intelligible AI. So they're trying to avoid the problem that you might have an AI system steering a drone, for instance, and you don't understand the mechanisms which it's using in order to determine what it will do next. And you want to understand those mechanisms because it's a matter of life and death, and you don't want to kill people without having good reasons. So they want reasonable, rational, intelligible AI, which means no labelless truth, no labelless information. And one avenue to create that kind of AI is precisely using ontologies. And that's what one of the things I'm doing with my image friends. So we should talk further. All right, so let's move on. So when I started working with the gene ontology, the other people were starting to build ontologies to work well with the gene ontology. So there are no diseases here. There is no anatomy, no lungs, hearts, no behavior, no environments, just these 3 things. And so we needed ontologies for other parts of biology. And I took hold of the gene ontology community for a brief period at this time and worked out with them a strategy for building suites of ontologies which are interoperable with each other. So not the linked open data hairball monster, but a very, very tightly coordinated ontology development process which will create interoperable ontologies, all using the same principles. And we call this the Oboe Foundry. So we published this paper in 2007, and it describes how we created not just a set of ontologies around the gene ontology, and I'll describe that in a minute, but also a set of principles for building ontologies in a coordinated way. So, in 2015, the world has changed. It's changed even more since then, but since 2015. So there are still too many ontologies being built, because it's easy to build ontologies and people can get paid for building ontologies. There is too much redundancy. The ontologies overlap, and they very often overlap in an inconsistent way, which is a bad thing. And still there is no commonly accepted methodology. But everybody uses OWL, practically speaking. There are other possibilities, but even they are closely related to OWL. And we also have examples of ontologies which really work and are really used by hundreds or thousands of people and groups. And so we can use those examples as a stepping stone towards creating useful ontologies in other areas. And that's what I've been doing, basically, by taking the examples of biology and trying to replicate them in military contexts and in engineering now. All right, so the Oboe Foundry, Oboe stands for Open Biomedical Ontologies. And the Oboe Foundry contains best practices for building ontologies. And the idea is that we have a hub and we have various spokes. And the hub should contain the principles. The hub ontology should be an ontology which says how the world is to be divided. And I'll explain what that means in a minute. And the hub will then have various spokes, and the hub plus the spokes will create what we call a suite of ontologies. All the terms in the ontologies will be defined, but the terms in the spokes will always be defined using terms which go back to the hub. And importantly, we try always to reuse ontology. So if somebody has already built an anatomy ontology following these principles, everyone will be required to use that anatomy ontology when they build their ontologies. So if you're interested in lung disease, you have to use the word lung in the way it's defined in the anatomy ontology. Okay, but then people still sometimes need to build their own local ontologies. So the ontologies I just described, the gene ontology, for instance, these are reference ontologies. They're used by thousands of people who rely on them, and they're kept up to date. They're published openly, immediately, and everyone knows that other people are using them, so they get benefits from using the same ontology as other people. But then you may have a very local purpose for which you need a local ontology. You may be doing an experiment in your lab or a clinical trial, and it's so precise, it has to do with the effects of a certain kind of, I don't know, rock music in certain kind, I don't know, doesn't matter. You need a local ontology. The local ontologies are called application ontologies. The big problem is that the military needs lots of local ontologies about these particular groups in this particular mountain range with these particular chemicals. And if you build ontologies for each new local group, you will never have the kind of interoperability that will enable you to do reasoning across lots of data. And so the key is to ensure that even local ontologies are built using the same principles and drawing as far as possible on the content of the reference ontologies. So this is the hub and spokes, and towards the middle we have reference ontologies. On the outward outlying ends of the third order or fourth order spokes, we have application ontologies. They all follow the same principles. All the terms down here are defined in terms of terms here, which in turn are defined in terms of terms here, which are defined in terms of terms from the hub. Now, the Oboe Foundry is not the only example of an ontology suite. There are many others. These are just some, and you can see that nearly all of them have a hub. But one suite, two suites on this list, one is a marine metadata. The other suite is confusingly called suite, but it's misspelt. This is the Semantic Web for Earth and Environment Technology, which is a NASA ontology. It failed, so they're rebuilding it. With luck, they'll rebuild it so that it doesn't fail. It doesn't have a hub. Now, one might say that the reason why it failed is because it doesn't have a hub, but I would say that. Now, we'll go through some of these. Most of them have hubs. So we just talked about that one. This one we already talked about. These are some more. So these are military ones. The United Nations has a hub-based suite of ontologies. The Federal Highway Administration, various intelligence communities. We're working at the moment on a reboot of what used to be called the Common Intelligence Community Ontology. And you see that all of these are based on BFO again. We have a joint doctrine ontology which is based on BFO. Common core ontologies are actually maintained here in Buffalo. And now each of these suites gives you various benefits. So the suites basically contain modules. And if you have modules, you can get benefits because of division of labor. All the mouse people can work on the mouse ontology. All the lung people can work on the lung ontology. And you get expertise then devoted to the corresponding ontology. And that's what the Oboe Foundry basically showed was possible. You have a division of authority. So some people are responsible for the lung ontology. Some people are responsible for checking that all the ontologies are linked together properly. That's two quite different kinds of authority. And that means two different kinds of governance for an ontology. And with different kinds of authority goes also different kinds of ownership. So some people are very thoroughly invested in a particular ontology and they want to control it. They are also people who other people rely upon to know what they're doing. And so they want that person to control it. And that motivates users because they trust. It motivates the owner because the owner can control it, but it motivates users because they trust the owner. It also, having modules means that the ontologies are discoverable because everyone knows where to go to find the lung ontology. There isn't a lung ontology, by the way, it's just an example. It also means that you can have a nice incremental approach because each ontology is developed incrementally, but the basic structure which separates them, as in the case of the gene ontology already, stays fixed. You can have new ontologies added, but you can't change the basic structure of the existing ontology, except in very, very special circumstances. And now, one way in which people had thought one might address the redundancy problem was to create mappings. So the linked open data hairball is supposed to be a collection of mappings. Those mappings never worked. And you can see why they never worked. That you're mapping between thousands of things over here and thousands of things over there, both of which are changing, but at different velocities. Both of which are run by very busy people. No one is going to take the pain of keeping mappings up to date when ontologies change with different velocities like that. And so the mappings die. And this just is a fact. Mappings don't work. We want to get rid of mappings and just have reference ontologies which everyone trusts. All right, now these are some examples of principles. I think I'm repeating here.
Can an ontology work if everybody isn't playing along? So, there's you work in an industry where there's other businesses and they have something. Could an industry create an ontology and without mapping? Like how do you do it when people don't want to play along?
So that's a complicated question. First of all, the gene ontology is still working in all kinds of ways for biologists, even if they never heard of it. Because, for instance, they're using statistics which have been assembled on the basis of the gene ontology annotation database. Secondly, I think probably it works best to have the ontology under the hood wherever possible. So the ontology can be working, but no one need necessarily see that it is working, because the car that they're driving is driving perfectly well. They don't need to look under the hood. So I think your problem, you're assuming that there is a problem, and there shouldn't be. However, there are cases where the car doesn't work. And the example and this is a very well understood example by now, two big companies merge. They each have different database systems. How do you get those database systems to work together? That is a case where you really need to have something like a dedicated focus of important representatives from both sides to ontology problems. Whether they use the word ontology, that's unclear. Whether they build an ontology is also unclear. But certainly the people who do use the word ontology and who have built ontologies have recipes for solving some of the problems which arise in those kinds of cases. Okay, all right, so let me just do a very quick rundown on definitions now. So in the olden days, people talked about genera and species. So mammal is a genus and lion is a species. And that is a key to understanding how definitions in an ontology work, because the species-genus relation is a specific sort of ISA relation. Now, how do you define lion? Well, a lion is a mammal which, and then you give a list of distinguishing features of lions, and this is where facets may indeed play a role. The idea is that the list should be formulated using terms from other ontologies. But the term which is the genus for your species term should be in the same ontology, and it should be one level higher. So if I want to define B1s, then I define them as A's which C, where C is the specific difference. This is a very old strategy for building definitions. It goes back all the way to Aristotle, but it's now become a kind of de facto standard within certainly biological ontologies and with other ontologies that I'm involved with. So, another rule when building ontology hierarchies is that you should bend over backwards to try to avoid multiple inheritance, which arises when one term has two parents. If you have an ontology with something like that in it, it's a sign either that you are working with an application ontology where it's good enough not to follow the rules religiously, or you've made a mistake. Now, it could be that there could be in Ford a division which divides cars according to their color. And for that group of people, an ontology like this is perfectly good and perfectly acceptable also from my point of view. But that group of people has very special needs. Normally, that would be a sign of a bad ontology. And what you would want is an ontology that looks much more like this. We have kinds of cars, and then we join the two ontologies together to create this for a special application need. But these are the reference ontologies which people maintain for reuse over and over again. All right, now I'll show you how this works with a toy example. So we have military vehicles. We have a definition of vehicle. A tractor is a vehicle used for towing, and a crane is a vehicle used for lifting and moving heavy objects. A vehicle platform is a means of providing mobility to a vehicle. And a wheeled platform does that through wheels, and a tracked platform does that through tracks. These are all reference ontology definitions. But then we have application ontology definitions. For instance, a delta battery artillery tractor is an artillery tractor used by the delta battery. Okay? This is not rocket science. Now, when I talked about car color ontologies, I said that they were normalized in this slide. So here the normalized reference ontologies look like this. First of all, we have types of vehicle. I'm just giving you a fragment. And then we have types of use of vehicle. And here we have an official military taxonomy, which we can use. It's already in good shape. So there are different components. There is an artillery component, an armor component, an infantry component, an aviation component. So an artillery tractor is a tractor used by the field artillery component. And these are branches of the military, if you like. And so we have a wheeled tractor used by the field artillery component. And now we have the beginnings of a link between two ontologies. The first is an ontology of military branches. The second is an ontology of types of vehicles. And so that will create what we call a defined class, wheeled artillery tractor. And then we can have an instance of that class, which is an instance of one field artillery component, which is the delta battery. It's a certain group of people with certain capabilities. The delta battery is an instance of field artillery component, and there is a wheeled tractor used by the delta battery, which was the application ontology term I referred to on a previous slide. The delta battery wheeled artillery tractor down there. So this is a combination of reference ontology and application ontology, and we show in this paper how to use those combination ontologies in order to do reasoning in a very flexible way when we find new information both about our own vehicles and about the vehicles of the enemy. And that is the end of part 1. So I have 1 minute left. And I guess we can just break for coffee and swimming.
So we'll reconvene in about 15 minutes, okay?